let me start with two quotes to get us oriented. One may not be an exact quote, but it was very striking. I tried to remember it. If you want to know what really exists, take your best physical theory and look hard at the mathematics. That quote was me yesterday. So the second quote, the second quote is absolutely precisely literally accurate. Yes, but first think hard about the mathematical tools you're using to represent the physical world. That's me right now. So let me go into just some very basic distinctions about the position you can take toward time. So, and generally, if we ask whether something exists, it seems to me there are three sorts of answers that are possible. One is simply that it doesn't exist at all. This might be a correct way to think of Julian's view, like leprechauns and Newtonian absolute velocities. There just are no such things. The second is that it does exist, but in some sense it's not fundamental, like pianos. We've got a nice piano there, it really exists. And protons, not fundamental in the sense that you think that all of the properties of the piano are consequences of the way the parts of the piano, which are not themselves pianos, are put together, and all of the properties of the piano are explicable in terms of those smaller things. And then there presumably ought to be some things, right, that exist and are fundamental, that are not composed out of anything else. What are the examples of those? That's obviously, you always have to have question marks around this. Maybe strings, according to string theory, maybe space-time itself. Now, we can then ask, of time, is it real? You might have the radical position that it's not real at all. Maybe that's the right way to characterize Julian's position. You can have a somewhat less radical position, which is that the space-time manifold is real, whether it's fundamental or not, but the distinction between time-like, space-like, and light-like directions in the manifold isn't real. And that was something I was trying to convey last night, that you just have this sort of four-dimensional object without any preference in the directionality in it. You can say, well, there is a distinction between time-like, space-like, and light-like directions in this thing. It's a real distinction, but it's not fundamental. It emerges from something else. Or you could have the idea that there is such a distinction and that it is fundamental. It doesn't have any further explanation. We can ask the same question about the direction of time. And here, I think, as for the reality of time, the way I just put it, in the direction, a lot of physicists will split, and they'll go one way on the first and a different way on the second. I guess Sean would be an example. So we can say, suppose we think that time is real, we can ask, what about this idea that it's anisotropic, that it has a preferred direction? Einstein seems to have suggested that he thought that what his physics told him, or you can read this, this is a quote from a letter to Besso, that the direction isn't real, right? For us faithful physicists, the separation between past, present, and future has only the meaning of an illusion, although a persisting one. A more usual view is not that the directionality is illusory in that sense, but also it's not fundamental. So an example would be to say, well, the future direction just is, as it were, by definition or by analysis, the direction of increasing entropy. You'll notice what happens if you do that is that the proposition that entropy increases just becomes analytic, right? Because increases is itself a time-directed verb, and if the forward direction of time is by definition the direction in which entropy is getting bigger, then of course entropy can't decrease. That's contrary, of course, to the picture you have when you think, yeah, sure, it can, right? There can be fluctuations, and they're unlikely in some sense. They don't happen often, but they can happen. We could view, the final view is that the direction of time is itself fundamental, that it has no further explanation. It's a basic piece of the physical universe. Now, what I'm going to argue is, or at least present a way of thinking about the idea that both time and the direction are fundamental. And I take it this is the naive, everyday view, the one I was disparaging yesterday, and the one that, quite correctly, all the biologists and all the chemists and all the people thinking about evolution take for granted, right? That time is going on in a certain direction, and their job is to figure out why, as we go further into the future, things get more complicated or better metabolized or whatever. Newton's view, of course, was that time was fundamental, that there was no further thing in physics which explained time itself. So in the scholium, he writes absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external. The relative changes of things that Julian has studied so much, Newton, of course, called merely relative and observable time. What is time for Newton? Well, time was a collection of a linear ordered collection of universal moments, instants of time. And an individual instant of time for Newton was, of course, itself an interesting object. It was an object that was spatially spread out. So in a different context, in the context of actually a metaphor, giving a metaphor that won't concern us right now, Newton writes, the moment of duration is the same at Rome and at London, on Earth and on the stars, and throughout all the heavens. This is, again, fundamental to the picture that Julian was suggesting, because his shape space was the shape of these instantaneous global moments, and the shape was the configuration at that moment. What I'm going to argue is that that, of course, is contradicted by relativity, and that we can, in a way, throw that away, but keep the rest of Newton's fundamental view. And we haven't noticed this so well. So I want to say that this picture of time, and again, I'm not going to say anything about actually quantum mechanics here, this picture of time is implicit is a little too strong, but very strongly suggested, I would say, by relativity. What is fundamental in relativity, in the relativistic picture of space-time? What is it that has no further explanation? What is it that's taken at the beginning as a given structure, and that structure itself has no further analysis? Well, in classical general relativity, you always start with a manifold, a four-dimensional manifold. And that already has some geometrical structure to it. And the geometrical structure that it has is its topological structure. So there's a lot of, and differentiable structure. There's a lot of geometry in it, not yet, when you just start with the four-dimensional manifold, any metrical structure, any time structure, so on. If you start with that object, that mathematical object, then you're naturally going to begin thinking you have this thing that there are, no distinctions of time-like directions or space-like or light-like directions, but there's still a thing there with properties. And then you start adding more structure onto that. You add metrical structure, you add affine structure onto that. Now, if you think about the idea of organizing points into a geometry, you have to, the organization has to take the form of putting structure on those points. And that structure you can think of as having a hierarchy. Metrical structure is sort of higher up in the hierarchy. Below that, an affine structure, by which I mean a straight line structure. So if I, for example, take Euclidean space, I can pick out the straight lines. If I uniformly stretch the space, all the straight lines will remain straight, but I'll change the metrical structure. So in a certain sense, the affine structure is less specific than the metrical structure. And below that, we have what's often called rubber sheet geometry, or topology. And essentially, what the topology of a space does is it specifies the structure of continuity in the space. And what I want to argue, and I'll try and do this, is that what we have used historically as the mathematical tool for understanding topological structure was a bad choice of a mathematical tool. That you can take the same concepts that are analyzed in standard topology, continuity of functions, connectedness, homeotope theory, and so on, and do them from a different foundation. Okay, so this is why this is a huge project. The project involves reconstructing all the mathematics that was done in terms of standard topology from a different basis, using a different fundamental notion, different definitions, and proving relations between these two structures. Okay, so I'm just going to give you a picture of what this looks like very quickly, and then apply it to some physics. Okay, so how does standard topology work? Some of you know this perfectly well, but for others I'll try and say very quickly. again, suppose I just give you a bag of points, a bag of atomic elements, and I tell you to organize them into a space. You've got to put some structure on them. In standard topology, this basic organizing structure is what's called the open set structure. Okay? That is what I do. So I'm trying to go faster. Let me go here. So the basic notion is the notion of an open set. And everything else that I define, so I'm now going to define what it is for a space to be connected, for a function from one space to another to be continuous, what the boundary of a set is, what it is for a space to be compact, and so on. Everything else that I define is ultimately boiled down to a definition in terms of the open set structure. So here's a kind of picture of the architecture of the standard mathematics here. At the bottom, you specify the open sets, or equivalently the closed sets, or equivalently the neighborhoods. Those are all interdefinable. Once I have those, I then tell you whether your space is connected, whether your functions are continuous. If we look at the spine running up the center here, once I have the notion of a continuous function, I have the notion of a curve, which is a continuous function from the real line into the space. And then I have the notion of a path, which is an image of a curve. So the notion of a path, you imagine if I have a point A and a point B in a space, and I say there's a continuous path that connects them, that idea occurs rather high up in a hierarchy of definitions in standard topology. Now, since standard topology runs on the idea of an open set, you want to ask yourself, what's an open set? What is the geometrical characteristic I'm trying to capture? And you always get, in any introductory topology book, an informal explication. So here's one I really like, right, from Crosley. An open set is a set where every point has some breathing space. Okay? So the idea is take any point in your open set and let it take a deep breath, and it'll stay in the set. Right? It's the other, and if you want to know what people think, not what's true, but what people think, you go to Wikipedia. And when I first did this, this is not up there anymore. This is what Wikipedia said, which is really beautiful. In topology and related fields of mathematics, a set U is called open if, intuitively speaking, you can wiggle or change any point x in U by a small amount in any direction and still be inside U. In other words, x is surrounded only by elements of U. It can't be on the edge of U. And so that fits the idea that you had of an open interval where you take, say, an interval in the reals and remove the endpoints. And then every point that's in there has other points in the set. Every number in there has other numbers in the set, both to the left and the right. Now, that informal notion of an open set, of course, doesn't do you any mathematical good. Mathematics doesn't run on the informal thing. What you need are some axioms. And if you think about the intellectual structure here, if everything's defined in terms of the open sets, and the open sets aren't defined in terms of anything more primitive, what gets you a grip on the open sets? It can only be structural relations that relate the open sets to one another. Right? So there are structural constraints on the totality of open sets. And in standard topology, the definition of a topological space is just any collection of points together with a collection of subsets, which are the open sets, that satisfy these four constraints. And the four rules or four constraints, this is, again, just, taken right out of a book. The whole set is going to be open, has to be open. The empty set is open. Arbitrary unions of open sets are open. And finite intersections of open sets are open. That's it. Now, you might pause for a second, although I don't have the second, to reflect what connection these axioms have to that intuitive notion. Right? So you had this intuitive notion that in an open set, there's no boundary points. Every point is surrounded by other points in the set. How is it that these four axioms convey that? If it's obvious to you, I congratulate you. Notice, a little thing to notice about it, which is cute, is that the only difference between T3 and T4 having to do with intersections and unions is that in one case you take arbitrary unions, and the other you only take finite intersections. And the structural conditions for a closed set, you define a closed set as the complement of an open set. The structural conditions for the closed sets are just the same, except you switch arbitrary and finite. And again, if you can see why that switch should take you from the concept of an open set to a concept of a closed set, congratulations. I don't. OK, so why should this actually get us to these intuitive notions of geometrical structure that we're trying to recover in a formal way? All right? And the second question is, why should this apply to the physical world? Why should this be a good mathematical tool for understanding the geometry of the physical universe? If the foundational structure is an open set structure, then the answer to that ought to be that there's something in the physical world that creates open sets or constitutes open sets. What would that be? Okay? I claim it's not obvious what that would be. Okay? Now you could, again, just be primitivist about this and say, well, of course, all explanation has to come to an end. There has to be some structure that has no further structure underlying it. Why not let it be open set structure among points in space-time? But I think that should be a last resort. Now, here's the deal. I'm going to reconstruct this whole thing from a different geometrical primitive. Everything. And the primitive is a natural geometrical one. It's the notion of a line. And the notion of a line I want you to have in mind is an open line in the sense of one that doesn't close back on itself. I don't care whether it has endpoints or not. But take any line in a space that doesn't self-intersect. Okay? What's characteristic about a line? What's characteristic is that if you want to stay in that set of points and move continuously, at any point you have at most two directions you can go in. And to get from one point to another, there's a particular set of intermediate points you have to go through. So that's not true on a circle, right? On a circle, I can get from A to B in either of two directions. In an open line, I have to go through a set of intermediate points. Now, that geometrical structure can be captured very explicitly in terms of a set of axioms. So here's the alternative architecture here, conceptual architecture. This funny font is my font. And any words written in that font are my words. And that means I have Humpty Dumpty's prerogative of having them mean whatever I want them to mean. The reason I'm using a different font to indicate these terms is that they have an intuitive meaning that is already in the language before we try to formalize it. And I'm trying to capture these intuitive notions. So what I'm going to do is specify in a space a set of lines, these open lines. In terms of those, I will then define what it is, say, for a function from one space to another to be continuous. That non-equality tells you that my definition is actually formally different. There are certain functions that by the standard definition are continuous, by mine are not. In terms of that, I will define a neighborhood of a point. This also will be different than in standard topology. So the neighborhood structures will not be the same. I'll define what it is for a space to be connected. Again, this will be different from the standard. It'll actually give you different results than in standard topology. Once I have defined the neighborhoods, I'll define an open set structure. This is now high up on the hierarchy rather than sitting at the bottom. Most of this stuff I can't talk about because I don't have time. I'll just run up the basic spline. So here's the main mathematical tool. And again, this will just be reminding most of you, is the idea of a linear order among a set of objects. It's any condition that satisfies the three conditions of antisymmetry, transitivity, and totality. If you don't know that, you don't have time to learn it now. Once I have a linearly ordered set of objects, I can define an interval in that. This definition, as far as I know, goes back to Dedekind. So you have an interval if you have a collection of these points such that for any pair of points, all the points between them are also in the set. So that corresponds, if you think of the real numbers ordered by the greater than or less than relation, the intervals are just what you'd think they are. They're the sort of closed, they're the continuous sections of the real line. They could either be open on both ends or closed on one end or closed on both ends. So here are the axioms. So this is just going to follow the general form of standard topology. So a linear structure on a set, you've got a set of objects and a collection of subsets, lambda, we'll call the lines, that satisfy the following four axioms. A minimality axiom that each line contains at least 2 points. This axiom, the segment axiom, which does a heck of a lot of the work, it says that for every line, so again, in your mind, just picture a line. The point is that lines are made up of shorter lines, right? Unlike open sets. Open set, you can have a big open set, and it has no open sets as parts. But if you have a line that contains a lot of points, some subsets of that, exactly certain subsets of that, will also have to be lines. And the way you get at that is saying if you have a line, there's a way to order the points so that all and only the subsets of that that are lines are intervals in that linear order. Okay? Now, what does that mean? It means this is a much more powerful and constraining axiom. So, for example, if I have a single line that contains an infinite number of points, I must have an infinite number of distinct lines in order to satisfy this axiom. So this puts a much stronger constraint on the structure than any of the axioms of standard topology do on the open sets. So this axiom relates lines to smaller parts that are lines. I then have an axiom that you can intuitively, if you have two lines that share an endpoint, you can union them together and get a line. You have to worry about, you don't want to form a circle, you don't want to close it on itself, so there's a little proviso in here for splicing lines together. Again, I don't really have time to go through it, but if you think it through, it's the right one. So if I have lambda and mu are two lines and they have in common only a single endpoint p, then their union is a line, provided essentially there's no short circuits, which you can define in that proviso. And there's a final axiom, which is there for aesthetic purposes I don't have time to talk about. Now, how did I use a linear order here? I said, in order to be a line, a collection of points there must be a way of ordering them so that all and only the lines that are subsets are intervals in that linear order. If you do that, it's obvious that if there's one linear order that does that, there's exactly one other one, namely the inverse. Because this linear order and the inverse, like using greater than rather than less than, will give you all the same intervals. But those are the only two linear orders that will agree on all the intervals. Okay? Now, this theory applies perfectly well to discrete spaces. So it's a mathematical tool, unlike standard topology, which doesn't really apply in a useful way to discrete spaces. So here's an example of a discrete space. I've got a square lattice. You think of any 2 points that are connected by a blue line are minimal lines. That pair of points constitutes a minimal line. And then this point splicing axiom will tell you, for example, that all of these ones that run up the pink or run across the green or run around the red, that'll constitute a longer line. So I have now this collection of lines. Now, once I have the lines in a space, I can define a neighborhood of a point. And it's a very natural definition. So the idea of having a neighborhood of a point is that the point is surrounded or protected on all sides by points in the neighborhood. So we can say that sigma is a neighborhood of P if every line that ends at P has a segment that ends at P that sits in sigma. So the idea is if I try to get to P in any way I can get to it continuously along the line, I have to enter the neighborhood and be within the neighborhood at least for a while. So that's a well-defined notion of a neighborhood. Again, on my lattice, if you look at the green point in the middle, the 4 red points together form a neighborhood of the green point. Because any way I could manage to get to the green point by going step by step along that lattice, I would have to enter the neighborhood. There would be a terminal segment that sits in that neighborhood. Once I've defined a neighborhood, I can define an open set. A set is open if it's a neighborhood of all its members. Okay? Now, you're going to see, if you open up a standard topology book, you might see that very sentence, but without my typeface in it. And it means something different in a standard topology book because the word neighborhood means something different in a standard topology book. In a standard topology book, neighborhoods are defined in terms of the open sets. A neighborhood has to contain an open set that contains a point. I didn't define a neighborhood that way. So this is, again, just materially different definition. So the picture now is, if I take a set of points and put a linear structure on them, that linear structure generates a neighborhood structure. That neighborhood structure generates an open set structure. I can prove a theorem, which is that the collection of open sets so defined satisfy the 4 axioms of standard topology, so they really are open sets in the normal sense. Okay? So I put a linear structure on a set of points. I generate a standard topology on it. And now I can start to just run some numbers for finite point sets. So if I have, for example, if you look down, if I have 5 points, I can put almost 7,000 different standard topologies on it. I can only put about 1,000 distinct linear structures on it. And each of those generates a topology. Lots of them generate the same topology. There are only 52 different topologies that you can generate by this definitional scheme. So the picture is, you might say, that a topology you can't generate this way. My original thought is that it is geometrically uninterpretable. So these other topologies exist as formal objects, but you can't think of them as arising out of an underlying geometrical structure given in terms of these lines. In a two-point space, I'm just going to say this very quickly. In a two-point space, because I only have 2 points, I can only generate two things. I either put a line in there or I don't. I can only generate two topologies. There are 4 possible topologies. So then I thought, oh, this is interesting. It means standard topology is dealing with objects that have no geometrical interpretation. But then I thought about it some more, and I realized, wait a minute. Suppose what I've been doing is imagining these lines as sort of two-way streets. If you can get from A to B along a line, you can get back from B to A. But suppose I put a direction on them. Remember, I told you, if there's one linear order that works, there'll be the inverse. Suppose I make my lines directed. So in order to get from A to B, there not only has to be a line connecting them, but the line has to go from A to B. Then I can define a directed linear structure, which is very much like this, except the lines all have directions. And from that, I can now run through the same thing. An outward, to say that something is an outward neighborhood of a point is that if I start at that point and go away from it, I always stay in the neighborhood. To say it's an inward neighborhood, to say if I'm arriving at that point, I always get to the neighborhood first. So now I can define everything in a directed way. And what happens is, for example, with my 2 points, I now have 4 possibilities, because I either put an arrow from P to Q, an arrow from Q to P, or both. That generates 4 different topologies. And now, if I run the numbers, I find that every single topology I can generate by some underlying directed linear structure. But there are many, many, many more linear structures, directed linear structures, than there are topologies. So you're losing a lot of information if you only have the topology. And in fact, I can prove a theorem that if I have a finite number of points, I can generate any topology. That's not true for an infinite number of points. So I'm just going to skip over this. So the picture here is, now I think of the geometry of space as being generated by a linear ordering among points. And now if I go to physics and I say, well, what generates the geometry of space-time? The natural thing would be to ask, what gives me a linear ordering among events? Right? Is there anything in physics that we already are familiar with that would generate a linear ordering among events? And the answer, again, if I let me go back 1 second. I know I'm going to run out of time right now. My original question is, why think space is a 4-dimensional manifold? That means it's topologically like Euclidean 4 space everywhere locally. Why think that? Well, you might think that because the linear structure ought to be like the linear structure of Euclidean 4 space everywhere. But is that true? If we look at Newtonian space-time, we just don't think that all these lines I can draw in here are physically the same. Some of them in Newtonian space-time are all simultaneous with each other. Some go through time. Some lines, as it were, would go for a while through time and then go flat, and some turn around. Why think those are all physical? What about in relativity? Why think all of these are physical? In fact, again, I'm just going to skip this. The natural thought is to think that time itself is what generates this thing. So intuitively, that's what time does. It orders events. And in relativity, we have the relation between time-like or light-like related events that they have a definite temporal order. Now, in Newtonian or neo-Newtonian space-time, there is an order among events, but it doesn't generate a geometry. So if I go into a Newtonian space-time, and I say, give me a maximal set of linearly ordered events, linearly ordered in time, it means for every time slice, pick an event. And a typical such set, maximal set, will be a random scatter. It won't look like it has an interesting geometrical structure. But if I have a globally hyperbolic relativistic space-time, and I ask for the very same thing, I say, give me a maximal set of events. So I can't add any to it. A maximal set of events where they're all ordered by time. What do I get? The light cone structure means that every such thing looks like intuitively what we thought a continuous line looks like. Okay? Because the light cone structure restricts my choices in the way that the classical structure doesn't. Now, the physical suggestion is take these as the fundamentals of physical geometry. Take these lines. What that means is that, here's a picture from Sean's book. Sean says a time-like path is allowed for a particle, and a space-like path is not allowed. What I'm saying is the space-like path doesn't exist. There is no such thing in the geometry. Okay? Space on this picture is emergent. Space is non-fundamental, and time is fundamental. If we slice through the relativistic space given this picture vertically, like in the middle, you get a nice lower dimensional relativistic space-time, because you still have all these lines that live in that slice. But if I slice space-like, you get nothing, because no lines live in that space. Okay? So on this picture, the relativistic time structure is built into the deepest geometrical structure you have. There's nothing it emerges from. And if you ask what builds it into that, the answer is time builds it into it. The end moral of this is that the reason we weren't able to see this is twofold. One is that we were using standard topology as a mathematical tool for analyzing geometry. And it turns out not to be the right tool. If you start from that, you're not going to see the directedness in the object that you're working with, because you're not using a mathematical tool that's sensitive to that. I can make a distinction between an intrinsically directed topology and one that's not intrinsically directed. An intrinsically directed topology is only generated by a directed linear structure and not generated by any undirected linear structure. So I can make a distinction, but I don't know how to make that distinction using only the tools of standard topology. The other thing is that if you try this in a classical space-time, it doesn't work. So this mathematical structure turns out to have been built, as it were, for relativity, even though I wasn't intending to do that. And if you apply it to relativity, you get a physical answer to the question, what is the origin of the geometry of space-time? And the answer is the origin of the geometry is this intrinsic ordering structure that time itself provides.